Hi everyone. My teammates Hassan, Narendra, and I are going to talk about our project predicting hospital readmission for diabetic patients. Why did we choose this problem, or why does it matter? Hospital readmissions are stressful and costly for patients, and they're also costly for providers. For example, in 2014, a record-breaking fine was issued to 2,610 hospitals by Centers for Medicare and Medicaid, CMS, because too many patients had been readmitted in a short time. And those who are diagnosed with diabetes have a much higher readmission rate. And even if we can achieve a modest, like 5% reduction, there would be far fewer admissions at annual cost savings of $1.2 billion. CMS uses this metric called 30-day readmission rate as a critical quality metric to incentivize providers to give better outcomes under the value-based care program. So our goal is to predict and prevent risky readmissions. Can we identify high-risk diabetic patients before they return to the hospital? My colleague Hassan will take and talk to you guys about our data set.
Hey everybody, let's talk about our data set for predicting diabetic patients' readmission. So this data set comes from 130 US hospitals, and the data set was recorded from 1999 to 2008. The data set has 50 plus features, and we saw that the majority of the patients are older and primarily Caucasian. Most hospital entries occur via emergency visits, which suggested that they were acute health events. For the categorical features, we found that patients discharged to Medicare swing beds showed elevated readmission rates. Frequent diagnosis categories were circulatory related, diabetes related, and respiratory related. Neoplasms were more common as secondary, tertiary diagnosis than readmitted patients. For our medical analysis, we found that insulin is the most prescribed drug with 53%, and then triglyceridone and acetohexamide usage showed highest reduction in readmission risk. As Boski stated earlier, our target variable was the patient readmission under 30 days. Moving on to our next slide. For the data quality challenges, it was expected that we'll run into some data quality challenges because with hospitals, we could have those issues because um, it's it's just the nature of how things run in a hospital. So, for the fact that our target variable was patient readmitted under 30 days, we realized that only 11 out of 100 diabetic patients were of that category. And so why it matters is because though the category is low in number, we do realize that this is not a high occurring event. Therefore, that was a challenging piece for us that we realized. And some of the other things that were also missing were the patient's weight, their glucose test, and their diabetes control measures, which we thought were very important for predicting readmissions. Moving on to the next slide for our feature selection and engineering. For feature selection, we thought that we should just run some plot analysis to see which of the variables are predicting the target variable, and inpatient visits, emergency visits, the types of diagnosis count, and the medication count were some of those features that were strong correlations to the target variable. Among that, we also noticed that prior visits are strongest predictors. More diagnosis, more medications were also linking to higher readmission. And then patients who were older were getting readmitted at a higher rate. For the medication piece, we realized that insulin and replegadenide were increasing their readmission risk, whereas triglyceridone and acetohexamide were reducing the readmission risk. And to the feature manipulation, I'll hand it over to Narendra to talk about it.
Thanks, Hassan. Well, in this slide, we show how we transfer our transformed and enrich our raw data into model-ready inputs. Some of the key highlights are binary target. We recorded readmission into one for less than 30 days and zero for otherwise to eliminate some of the data sets. And then we also have implemented 10-year age bins into numeric midpoints. By doing so, we make sure that we have readable data. And then we also have added a flag for 75 plus to capture the elderly vulnerabilities. IDC 9 grouping, we basically have hundreds of diagnostic codes which we collapsed into core categories like cardiovascular and endocrine, improving signal to noise. Similarly, care churn matrix, total visits and visits rate summarizations, a patient system use. Basically, it's reflecting to ongoing instability in the data, and also admission intensity ratios. Basically, procedure per day and labs per day help distinguish any complex stays from the routine ones. And lastly, admission discharge mapping. Converting numeric codes into emergency or electives basically gives model a clear context on the how the care pathway is working. Together, these engineering features basically injects the clinical insights directly into learning algorithm. Let's dive into model implementation and some of the key highlights on the model selection. So our very first step was to deep dive into EHR data. We had 17 categorical fields and some of the, as we talked about, some of the ICD 9 groups where we have converted code into actual groups. Alongside basic idea is to alongside having this categorical data and 14 numerical measures. Basically, we have faced sporadic also in this data set. We also faced the sporadic missing values. And some of the key columns we found, and we come to know that the only 11% stays ended for 30 days readmission. So it was a highly imbalanced data set. And basically, this profile of mixed data type and missing some of the data values as described earlier resulted us to qualify two of the major algorithms or models like CatBoost. And between them, CatBoost is stood out for its ability to ingest all 17 category directly without any manual encodings. And basically also it automatically weight and underrepresent randomness class. So it is stop itself when it starts to overfit. So that's why this cat boost was highly suitable for this EHR data set. Yeah, a model implementation. Basically, in this, how we have prepped our data, we choose, as we described previously on previous slide, how we choose this cat boost model for implementation. Basically, we again to reiterate, we built in handling of categorical data sets and class imbalance. This was some of the key points highlighted in this slide. Like we have data splits stratified with 80/20 training and testing to preserve the 11% positive rate. We also leverage the cat boost auto detects our categorical classes or columns and no manual hard coding needed. Another is the core tuning we have done by 1,000 boosting rounds and then early stopping after 100 rounds of no gain. So with a depth of 7. Basically to capture all the moderate interactions. Also class weights to penalize misclassification of readmit patients. So to model takes 11% minority more rigorously, as we described previously in the points. And sampling and regularization, basically making sure that we have subsample of 0.8 and the call sample of 0.8, keeping overfitting in check all the time. That was our goal. So to do that, we also implemented threshold sweep. Basically, we wanted to maximize our F1 score and wanted to harmonize between our precision and recall scores. So that's what we implemented. So instead of having a fixed 0.5 cutoff, we've tested the threshold from zero point 0.1 to 0.9 to maximize F1, and we landed on 0.4. So this was our sweet spot between the precision and recall. This configuration balanced the detection of high-risk patients and overall model stability. Okay, in this slide, we basically let's review the CatBoost model results. Some of the key metrics. So the accuracy and discrimination, 81.2% overall, we achieve accuracy with the optimal cutoff as I was describing previously of 0.4 and AUC ROC of 0.64. This is well above the random score of 0.5, and so the model performed well in this case. Similarly, F1 performance score was 0.23, which is good and shows the stable result, and reflecting our balance of precision 18% and recall rate of 32% for 30 days readmissions. In plain terms, we correctly flag about 1 in the 3 readmissions. Threshold tuning, one of the highlights. Basically, we have, as I explained, 0.10 to 0.90 shows 0.4 optimized that F1 score. Some of the key top predictors are basically discharge, disposition, hospital intensity, medical complexity, and so on and so forth. On the other than that, I think clinical impact-wise, if I talk, catching up 32% of high-risk patients, hospital can definitely target follow-up resources more effectively, potentially preventing any readmissions as such. Handing over to Hassan.
All right, so in terms of the key findings, as Narendra stated, CatBoost had better discriminative ability. For our final performance, we had 81% accuracy and 32% recall for our high-risk patients, which is the readmission under 30 days. So critical insights, a model identifies 1 in 3 high-risk patients, and the top risk predictors were discharge, disposition, hospital intensity, medical complexity, and the lab procedures. These all relate to how much attention the patient got while they were at the hospital in terms of the number of lab procedures that were done on them and the medical and the medications that were prescribed. Again, these patients were older than 75 that were at a high risk of being readmitted under 30 days. As stated earlier, we did apply SMODE technique, but our results were not satisfactory, so we had to resort to our class weighting within the CatBoost model. And then we're also taking a trade-off for precision. At 18%, it's not too great, but looking at our 32% of readmission cases for our recall class, we are satisfied with this prediction. Going forward into our next slide, so our future directions would be to just improve the data. To start off with, we would like to focus on longitudinal data to capture temporal patterns, enhance features with additional information such as time series labeling and clinical notes, and explore ensemble methods to improve the prediction power of the models, and then develop imputation strategies that leverage the domain-specific knowledge for handling missing values. Now I'll hand it over to Boski to cover the technical aspect of this presentation.
All right. I'll take us through our Jupyter notebook, and I'm going to focus mostly on our technical approach as my teammates have talked about the rest of it. So our first step was data understanding. We looked at what was missing, and and identified key columns or key features that were missing. We looked at our target variable, very important to understand that. And as my teammates pointed out, we have a high imbalance, 11.2% only of the patients readmitted to the hospital within 30 days. We looked at the numerical features first, trying to understand their distribution just by themselves to understand the patterns of data. We looked at the box plots to identify like variables that have a high outliers, for example, number of emergency or outpatient. We looked at the correlation to understand how these numeric variables are correlated with our target variable, again, with the goal of identifying which ones are really important for our feature selection. So example, number of inpatient. For categorical features, do a little bit more pre-work, some mapping here to understand, what these values really mean. Similarly, for our ICD-9 codes for our diagnoses, those were like too many, so we grouped them into diagnoses groups. So here we have the distributions of the various categorical variables and also how they're distributed with the readmission rate. We had to do significant work to analyze medication features. There were many medication features. We only chose the ones that had good patient representation. And we looked at the top medication usage. We looked at readmission rate by number of medications. But a very interesting analysis we did here is to understand how medication change within the admission period affected readmission rate. So that gave us some good insights for feature selection. Once we had good understanding of the data, we handled missing values, removed the columns that had too many missing, imputed others with values like no test taken or missing. We handled duplicates. There were patients with multiple encounters, so we picked ones that were wouldn't leak into our model in the test data. Then numeric conversion of the age, right? So like my teammates mentioned, we created some enhanced features to kind of, because there were a lot of there's a lot of complexity, medical complexity. So we wanted to capture all those complexity and risk and intensity. So we had that. All in all, after that, we have basically prepared a feature set, chose our variables, and we were ready for modeling. 2 models, like my teammates said, both the models, key things, we were using AOC for evaluation, well suited for imbalance classification. We use the native weighting flags. We use the native categorical processing, so we didn't have to do one-hot encoding. And for both, we evaluated the feature importance, where you could see that, like for this one, like for XGBoost, the diagnoses were more important. Whereas if you scroll down to the results for CatBoost, discharge disposition, hospital intensity, and medical complexity were the top features, and probably explains why CatBoost performed better, because I think the XGBoost overfitted on the diagnosis groups. So our deployment plan. So our deployment plan is to actually, use this as a real-time API. It's integrated within the EHR, this is a sample input and output of this API. The overall architecture is such that the EHR makes a request to our load balanced API using fast API implemented in Docker, which is a container model. And all of this is hosted on AWS. So we're using an ECS managed service. We're going to deploy the model via GitHub Actions. And our training and test data set lives in S3, so it's accessible to everyone. This model, of course, doesn't take into account, model drift and also just how, just versioning. All right. So overall, I think we have a strong model with the 32% recall rate. But, like Hassan pointed out, we need probably more work to make it even more useful. Thank you.